Thank you so much. Good morning, everyone. I'm Michel Kamel. I'm from France. I'm working in École des Mines de Saint-Étienne and University Clermont, Auvergne, Lyon. And also in collaboration with Beyond. Beyond is a US company working on helping telco operators automating their network, monitoring it in a smart way. And my active research currently is around anomaly detection in the network, in the telco network, and specifically based on alarms data. For the plan of today, we'll first discuss the network data and an overview about the source of that data, why we are doing anomaly detection, and then going to methodology that is based on alarm data. First, the mathematical formulation of it and the methodologies and result and conclusion. And we will end up the presentation with a perspective. From network side, so everyone here is using a communication, an internet connection through a certain network. And imagine in a country where you have a telco operator, we have something that is called core, and we have some branches and connectors and servers to antennas, and antennas are connected to users that are residentials or mobile phones and others. So this is an illustration of how the network is going, and it's much more complicated than this because you have thousands of cells and you have thousands of these connectors that can be either wireless or through cables and others. And at each point in this network and connectivity, you have some data that is going back and forth in a very high speed and a very high volume also. It's a big data that is continuously moving back and forth in the network. And telco operators are interested to understand this data as quick as possible, generate value from it, model it, insights, and others. In our case, we are interested in anomaly detection, which means that whenever we have any underperforming cell or connector or core or whatever, we want to detect it quickly so they can fix it. And a human cannot do that. That's why we need machine learning algorithms to be running on this network to understand this data. The type of data is varying between numeric, textual, and structured and unstructured data. In the case of alarm, which is our case, this is events data that is generated whenever something happens at any point on this network. Why anomaly detection? Because the network is running and you have a certain normal behavior when people are talking or are using the internet in a normal way without any issue. But whenever they are facing problems to connect or to use that connection or any disconnections during calls or internet and others, this is an abnormal behavior. It cannot be a normal. And we are trying here to use statistical mathematical methods to model the normal behavior so we can directly flag any abnormality. And this is a characteristic that can be related directly to statistics, that occurrence of anomaly is something a rare event, and it's not something usual and shouldn't be, because if it is usual, then it becomes a normal and the network is not performing anymore. Anomaly detection also opens the door for other use cases that are predictive maintenance, root cause analysis of these anomalies, and others. Anomaly detection also, to do it well, we have a different range of models and theories to tackle, from machine learning, deep learning, to statistics, and information theory and others. One other important aspect is the subject matter expertise on the network, which are usually telco engineers. They understand the network, they understand the data. They are not data scientists or machine learning experts or modeling experts, but they help a lot in understanding the data so we can play with it and use it. And the last concept that is important also is the difference between an anomaly and an outlier or data outlier. Sometimes the data going over this complex network can generate some outliers due to a system underlying and whatever. And it's very important to differentiate between anomaly that is leading to a business problem or customer satisfaction issues versus outlier. Moving to our focus here, alarms data are events data and very important source of information. So, for example, network engineers currently look at this data to know what is happening, although sometimes they cannot look at it because it's a huge data coming from everywhere. And in alarm, data is a categorical data, a structure event data. And we can think as a binary random variable for each alarm. We have hundreds of types of alarm, but each alarm, if it's happening, it can be yes or no, binary random variable. And it has a certain probability, and that probability depends on many other factors that can be modeled. In our research here, we created 4 signals or features that are calculated from the raw data and then aggregated in a way on each interval of time to start saying something about the underlying data. And those 4 features are number of alarms in, let's say, in X number of minutes. How many alarms do I have on each network element? And this number of alarms is following a Poisson distribution. We did many statistical tests to confirm that based on the historical data. The second feature is the inter-arrival time between alarms. So if I have an alarm happening now, when is the probable arrival of the second alarm, of the second event? And this is following an exponential distribution. Then we have the transition probability between 2 consecutive alarms in terms of their type. An alarm of type A can happen now, but after a few minutes, the other event can be of same type or different type, B or type C or whatever. And this is following a Markovian transition model. And the 4th feature is about historical frequency, because if an alarm is happening now, historically, how many times that alarm happens. The more it happens historically, the less important is in terms of anomaly. And going deeply into each signal, first one is the number of alarms. This is a mathematical representation of it. And we estimated the rate parameter lambda of the Poisson distribution for this random variable. And then we transform it into a signal and a score. And this score is represented in this formula, normalized with this denominator thing. And this signal, the higher means the more probability of having an anomaly. And the second signal is about inter-arrival time, which is following an exponential distribution. And then we estimated also the parameter mu of the exponential distribution. And then we created the second score, which is represented by this formula of probability, also normalized over the whole data to get a score between 0 and 1. And this is the cumulative distribution function of exponential distribution to get all probabilities. And then for third signal also, which is transition probability, we created this transition matrices and we estimated probability PAI-AJ, which is probability of seeing AJ as an alarm after AI for all I and J. And then also we generated the third score and also normalized to get all between 0 and 1. And the fourth signal is about historical frequency. It is the frequency, the score is calculated using this formula, where the probability is the maximum of 1 over frequency. So if an alarm, the more if an alarm happen historically, the less probability we have here. And the higher, the less score we will get from this signal. So having these four signals and then transformed into four scores, the final score is a combination of four scores. We do it here a linear combination, weighted combination of four scores to get the predictive one, and then how to optimize these weights and see what is the optimal way to maximize the accuracy here of this final score. We labeled a set of data by seeing when it is anomaly, when it is not, and then we used a grid search to maximize the accuracy based on these labels and over W's, and then we get the best weights for this combination. And all what you have seen is based on has been applied on a real-world data from a virtualized telecom network. We identified all probabilities based on that data. And we tested also all assumptions, especially the Poisson and the exponential distribution using some t and chi-square tests. And then we generated the final weights and final score for each time interval. And then we did that on that data, the optimization that I mentioned. And here we can see the ROC curve. And this is the confusion matrix, where we have this 531 and 103 that are mispredicted by the model, being not anomaly where they are, and vice versa, while 2521 are anomalies and really predicted anomalies, and these are not anomalies and really predicted anomalies. So we got really very good accuracy score of 97.5. And those are the weights we got on one big sample from the data. From conclusion, the advantages is this is a kind of a non-line anomaly detection model, and you can think of it as any new arrivals are directly processed by all scores and formulas and classified as an anomaly or anomaly. And then this is based only on alarms categorical data. And that's something highly important, because usually anomaly detection algorithms are based on numeric KPIs. And it's not common to use these to help subject matter experts to maintain very good network and quality of service. And then the interpretability of this model is key. It's kind of open box, white box model, where experts also can understand the reason for a high score or a low score or an anomaly and others. And then next steps on our research, we are now will be working on developing a tool for root cause analysis based on these signals and anomalies. And then we will go into more probabilistic behavior of these anomalies and use some extreme value theory to understand how we can solve other problems. And also mixing this alarms that are events data with logs and textual unstructured data from the network to capture different areas of the network and of anomalies. Thank you so much.